First section, I'm going to talk about what is the problem that we're trying to solve. The problem of IP Fast-Reroute and fast convergence, we've been working on this for decades. And so we've made a few enhancements over the last few years on how to converge networks faster and how even to do IP Fast-Reroute. So again, I'll talk about the problems that we're trying to solve and the foundations of the solution sets. Alia's going to talk about some advanced mechanisms of the solution, as well as some solutions to micro-loop prevention. Kind of come back, and the two of us will do a summary, and we've got some questions for you, and you'll probably have some questions for us by the time we're done. And then we'll take a look at the network analysis by Guggen's work at AT&T. So what is really the fundamental problem? The fundamental problem is that we are currently suffering in our IP networks and IP MPLS networks of a loss of connectivity when a link or node goes down or potentially is introduced into the network. We currently, as we all know, have no ability to distinguish what's important in the network, what we want to converge first. Can we protect certain assets? We need to solve this problem. Next, how fast can we converge the networks? Usually, in most IP networks, sub-second is really pretty good and meeting a lot of the needs. But there are applications that need to get down to sub-200 milliseconds. And the most famous one is probably voice over IP, and when you can hear a pop in your headset as something requiring roughly 200 milliseconds of convergence time. And then, of course, there's the ever-famous 50 millisecond nirvana. And as a vendor, no matter how many decades I've been attempting to convince all of you that we really don't necessarily need 50 milliseconds of recovery, you have absolutely convinced me that I need to solve this problem because I'm not winning, and you keep coming and talking to me about it. So what are some of the new requirements emerging? Well, when I first started writing code for routers, it was, Dave, please have your software stop oscillating traffic through different links as they're coming up and down, or just because your software is broken, can you please stop oscillating traffic wildly through my network? We think we've solved many of those problems. As long as it's still software and as long as I'm still writing it, one never knows what might happen, but we're really trying to cut down on these persistent long bugs that are actually destroying our ability to converge networks quickly. Voice over IP is the obvious service that many of you are trying to roll out, and we're trying to be able to build networks with you that can do that. Video distribution networks and video on demand, of course, is coming through with their requirements. And then reduce the impact of maintenance windows. Your time to do maintenance windows is getting smaller. Our time to load new software and get things working and qualified and verified is getting shorter, so we need to be able to recover very quickly, as well as begin to try and introduce some determinism in the way our software is running, the way the network is reacting to changes as the software is seeing it. So what's in our network today? I think there's been enough discussions over the last couple of years, 2, 3, 4 years perhaps, on how to do sub-second convergence in IP and MPLS networks at both Nanog and RIPE. And if you didn't happen to catch those, we can do some workshops again, as well as the slides are available in the archives. So I do recommend you look there. It's really how to tweak the timers. The default timers for protocols are completely misset for today's networks. But changing from a default that's been out there for decades to something new overnight generally is frowned upon by the operator community, meaning you. So a couple of other things that we know is we can get sub-second, and we think we can get sub-second network-wide. And we know that given certain scenarios, we can get sub-500 millisecond. But the problem is really we can't necessarily do it deterministically. It works potentially great in a lab, and it works under the vast majority of scenarios in which there's a non-network catastrophic situation. But when do we care about, of course, when do we care about convergence the most? During the catastrophic situation. Catastrophic situation is when multiple peers are going down at the same time, and your operators are trying to go in and grab SNMP objects and variables, as well as there's statistics being collected in the rest of it, causing the CPU to drive way up towards 100% or stay persistently at 100%. When your CPU is pinned, it means that it doesn't have time, obviously, to run reconvergence algorithms, and so determinism during catastrophic events is one of the most difficult things that we can try and solve in our routers. Also in your network today, I'm going to show you very quickly that sub-50 millisecond in IP networks is basically impossible the way we've engineered and designed these protocols. So why does convergence take so long? Quickly, at an abstract level, we know we've got detection time, which is in order milliseconds, report the failure up to the route controller, say from a Sonnet driver or whatever the case might be, is in single milliseconds inside a router. Generate and flood an LSP or LSA is, say, tens of milliseconds. Trigger and compute the SPF is tens of milliseconds. Communicate the new next hop to the line cards is hundreds of milliseconds, and install those is the amount of time it takes to update those registers. What's been discussed in the past has been the fact that SPFs take too long. And many, many people come and talk to me when I talk about routing protocol architecture or router control architecture, that how long does it take you to run the SPF? The SPF really isn't the interesting part. Of course, the larger the network, the larger number of prefixes, links, and nodes, potentially the longer the SPF is going to take, depending on the implementation. But again, it's really installing the new routes to the line cards in a distributed router that's the most challenging piece. So what do we really want to focus on? We want to focus on potentially running as few SPFs as possible and having new next hop already installed in that FIB. That's the general approach. Taking a look at a few numbers. The failure detection, as I mentioned, and this is on one of our boxes, we can see the detection of a failure in less than 20 milliseconds. In fact, I've been up here talking about a protocol I worked on with a good friend named Dave Katz called the bidirectional forwarding detector, and that protocol was invented to solve this problem. And the problem was meant to solve is how to detect failures at layer 3. It's not a link detection protocol, but a forwarding plane failure detection to cover not only things that Sonnet doesn't cover layer 3 obviously, but also to cover other L2 networks like Ethernet. Origination, less than 10 milliseconds. Queuing, serialization, and propagation, less than 30 milliseconds. Flooding, again, tens of milliseconds. And the SPF in our implementation is 40 microseconds per node in the actual graph of the link state database. The FIB update is roughly 100 microseconds per node, and then the FIB distribution delay is on the order of 50 milliseconds. Now, we happen to have a notion of important prefixes in the network and can be marked as such, which really what we're talking about here, of course, is the BGP next hops for internal BGP, and then can have BGP converge at the same time as the IGP, but the point is still the same. The larger number of important prefixes you have, whether they're distinguished or not, the larger number of prefixes you have that have to be downloaded, the longer the total convergence time is going to take. But as I posit here in a network of 1,500 nodes and 2,500 prefixes, it can be sub 500 milliseconds in today's network. But why can't we possibly achieve 50 milliseconds or below in today's IP networks? Well, we've got that pesky speed of light problem that nobody's solved for us yet. So we can detect things very, very quickly, but we have to be able to propagate the failure wavefront and the rerouting wavefront through the network to each node that actually has to reroute traffic around. Because there's this propagation delay of that pesky speed of light, we can see in this graph, which was taken from another Nanog presentation, the percentage of traffic rerouted and the distance and propagation time in milliseconds. And that right there, as I just pointed, was 50 milliseconds. We get a lot of the internet's traffic rerouted if we can propagate that LSA in time, but we also miss traffic. So we're basically positing that in today's internet, we cannot use the protocols as they've designed to achieve less than 50 millisecond convergence, if that's truly what's important. MPLS Fast-Reroute and Sonnet detection can do this. How does MPLS Fast-Reroute do it? Obviously through pre-computing the path that's supposed to be taken when there's a failure. So you take a local action to avoid the propagation and distribution problems at that node adjacent to the particular failure. So how is this related, again, back to MPLS, IP Fast-Reroute, and MPLS? And we'll talk about this a couple different ways in the next slides. We know that LDP is commonly used as a label binding protocol, obviously to bind tunnels to particular routes. There's some options obviously on the table. One is RSVP-TE, which is what everybody's using today because that's pretty much what's available. There's obviously pros and cons to using the different approaches. And with RSVP, we know we have to have a new protocol, and we know we have to potentially create a new overlay network. And there's a couple of other techniques we can use in MPLS. We can use IP in LDP Fast-Reroute so that we pre-computed in next hop as well for the label binding. Or we can use a combination of the two. What you're going to hear coming from me and what you're going to hear coming from my colleagues is that we are not advocating that IP Fast-Reroute takes over the world and replaces MPLS Fast-Reroute. That's really not the point at all. But IP Fast-Reroute does have a place in solving some problems in the network that perhaps MPLS Fast-Reroute can address or perhaps you don't want to deploy to address. So we know that MPLS Fast-Reroute obviously requires the supporting signaling protocols. We know that we have to set up our repair paths beforehand, and we know that it can create quite a meshy network. But what we're trying to present here, again, not as a solution to everything, but we're trying to present here is that IP Fast-Reroute can solve very similar problems in an IP-only network or in certain parts of the network. And it does it without explicit routing, which has its pros and cons, of course. The pros of using RSVP-TE and RSVP-based Fast-Reroute is that we know we can achieve link, node, and shared resource link group protection. It's been designed and built over many years now to provide just that. We know that we can provide 100% coverage except for ingress and egress node failures. And that's probably one of the most important places in a network design that IP Fast-Reroute has a place. We know that it's got a well understood and deployed technology today. Most folks who are using MPLS are using it, in fact, with Fast-Reroute techniques turned on. And we know that it provides bandwidth guarantees, which we also, I'll state now, that IP Fast-Reroute cannot do. But some of the cons. Obviously, you have to deploy RSVP-TE. Some of the cons. You have to deploy RSVP for Fast-Reroute, even if you're not running traffic engineering in your network. Can be moderately painful, although many folks have overcome this. We've got to build overlay networks and manage overlay networks, and there are single points of failure. And those single points of failure are area and autonomous system border nodes. The main components of the IP Fast-Reroute solution are kind of obvious. We need to pre-compute a backup path. We need to figure out the repair mechanism we're going to use, and we have to have a reconvergence mechanism. And Alia is going to talk about that in much more detail than I am, but I'll lay out the foundation of some of the solution. The general approach is equally well known and straightforward. We need to detect a failure. We need to invoke the pre-computed path. We need to have packet delivery restored using the pre-computed path. We then generate LSPs and notify other folks. We recompute in the background the new fib using loop-free convergence. We then need to solve some micro-loop problems that are there in today's network and that we've primarily discovered through the IP Fast-Reroute work. And what we believe we can achieve with this approach of using the pre-computed backup paths and then calculating the least cost path through the network while you're forwarding traffic in a loop-free manner can demonstrate that we can do this in 50 milliseconds or less. It's really the time to detect the failure plus a few milliseconds or less to go and update your pointers in your forwarding tables from the old next hops to the new next hops, and that's it. It's really a memory pointer update, depending on the implementation, of course. So the pre-computation strategy is kind of obvious, right? We need to pre-compute these things in advance. It needs to be pre-computed consistently across the network. But we also know that this pre-computation takes a significant amount of time. We are, in fact, running more SPFs in the background. We know that in today's networks, we're seeing microloops, and I'll describe a couple of scenarios shortly, and that the microloop properties are really dependent upon the size or diameter of the wavefront of the failure as it reaches all of the nodes that have to reroute traffic around that particular failure and how long it takes the specific implementation to actually update the fib. So we've got propagation time, we've got the implementation differences on how to update the fib, and then of course just plain how much data do we actually have to update in our forwarding information bases. The loss due to these microloops is in fact potentially longer than the time it would take to do the fast reroute. So microloops and solving microloop problems becomes a very, very critical step in IP fast reroute. What are we really talking about here, and what do you see in today's networks? And you see this when you're running an IP-only network, or potentially when you're running an IP and LDP network, when you have to do label binding to routes. What we really see is that when the link fails between C and D, C is going to reroute traffic the only way it knows how to get to any destinations behind D by sending it back to B. But we know that due to the propagation delay of potentially sending LSAs, that B is still sending its traffic towards C until it can receive that LSA, update its fib, and again, pass it in the correct direction as well. We see this today in all networks. No, I don't have 5 minutes. Oh. Okay, that's fine. I'm hearing myself talk. I'm getting excited. Yeah. So microloops on link up. Microloops on link up also occur. And these, of course, are much worse than link down. Link down, you want bad news to spread very quickly. And on link up, which is good news, this can spread more slowly through the network. But in fact, what we see is microloops today. When the link comes up between C and D, what's going to happen is that C is going to tell B, and D is going to tell A. Now, depending on the scenario, that LSP or LSA can reach A before B can recompute which direction it needs to send traffic, which would be to C. So in this particular case, when the LSP is received by A, and before it's computed on B, received and computed on B, A is going to continue to send traffic, or it's going to start sending traffic in one direction, and B is going to continue to send traffic in the opposite direction. And we see this in today's networks. So microloops do matter. It's not just a theoretical construct that doesn't really matter if we see microloops. In fact, we see them all the time. And what we do know is that the faster the convergence, the smaller the deltas. That's kind of obvious. The worst case is generally a few hundreds of milliseconds, as we saw, because it's based upon the diameter and, again, the speed of light of the propagation of the wavefront to the rerouting nodes. Now, we do know that solutions exist, and Ali's going to spend some time talking about these solutions. And then we can also add some protocol knobs, as you may have read it in some IETF drafts, to a notion of graceful shutdown and interface graceful shutdown in the protocol specifications. The repair path mechanisms really are pretty straightforward. Today we have equal cost multipath, which is known. We've got loop-free alternates. And when a neighbor has a path to destination, which doesn't loop back to us, we've got multi-hop repair paths when we can send traffic to a non-directly adjacent neighbor, but if the data was to be received there, it would naturally flow downstream. But in all cases, the path has got to work during and after convergence. So what's the foundation of the solution sets that Alia is going to present today? We can look at it with the most basic triangle topology and triangle design in networks. That we're talking about the failure between A and B. Because we know, or in this particular case, all traffic behind B is going to be sent from A directly in the link between A and B, of course. The key to this particular very simple solution basically has been known for about 30 years, which is if we can calculate that all the traffic that's going between B and D, if this link was to fail, could suddenly go up through C. And if we knew this beforehand, if we could calculate this beforehand, we can power slam all that traffic, if you want to think of it that way, from the link between B and D to the link between B and C, and that traffic will naturally flow in the correct direction. But we need to do this pre-computation. So as I mentioned, to solve this particular problem, it's purely a local decision. We don't have to signal anything. We don't have to tell the other side, because we can calculate that in this network topology, we can again power slam that traffic from one link to another. During that particular time that we've sent all that traffic, because we've pre-computed the path, we then can calculate a new least cost path through the network if necessary. The key to this particular solution is that you pre-calculate a non-looping path through the network. Not necessarily that it's the least cost or shortest distance, if you want to think of that way through the network topology, just that it's non-looping in particular. It requires certain network topologies, though, to solve the problem this way. What we see is that, yes, we know that the downstream routes are easy to compute, and we know we can populate ribs and fibs, because we've been thinking about this and theoretically looking at this for about 30 years. But we also know that network topologies of that particular shape aren't always realistic. According to some of the research we've done on very, very large service provider networks, this can basically solve 70 to 85% of all the topologies and achieve IP Fast-Reroute. Well, again, if you think about it intuitively, you'll understand that intra-pop, generally you have your meshiest connections. It almost solves approaching 100% of the problems. The problem is, of course, across the core, where links are less meshy, and potentially there's leafs out there where there's only single connectivity, of which there's basically no solution set in that particular case. So from these surveys, looking at this very simple solution, we can achieve, let's say, 70 to 85%. The key to the solution set that Alia is going to be talking about is that last 20%. And there's really a couple of classes of approaches that she's going to be talking about. One is a repair fib, and another one is kind of what we would affectionately call loose source routing, but it's loose source routing plus. So again, the overall framework that you want to keep in your head as Alia's talking, we want to pre-compute the alternates on the topology change. We want to use that alternate during the local failure, continue using that alternate until we've converged on the new primary next hops become available. We can use these alternate next hops for LDP as well as IGPs and IBGP. And then we can separately solve micro-looping inside the network, as we've discussed, that can persist for potentially hundreds of milliseconds. So I'll turn it over.
So first, let me talk about loop-free alternates, which Dave has already introduced. This is a little bit more of an example. It's not just a triangle topology necessarily. In this particular example, the traffic, S is the computing router. It can send traffic to reach D via E normally. If the link from S to E fails, S can use an alternate path sending it to NI. And this is all, as Dave said, computed using the link state database that it already has. What needs to happen? Well, the path from NI to D has to not go back through S. That's in order to use it at all. It has to not go back through the link between S and E, which is an issue if you have, a broadcast interface, Ethernet. And it has to, if you're looking for node protection, not go through E itself. If you want SRLG protection, you can compute that as well. It's a bit more information to drag through the SPF computation. But there's also, there are two pieces to the problem, right? First, you have to pre-compute your loop-free alternate and be able to use it. But you want to keep using it until the networks converged such that the new primary path is safe. So if you look at this particular scenario here, when the link from S to E fails, S decides, oops, that's off the screen a little bit, sorry. S decides to send it to, good heaven, okay, sorry. Sorry. This is the problem with being short. When the link between S and E fails, S decides to send the traffic to N1 as its loop-free alternate. That's great. But then if S goes ahead and converges, and it decides now it's going to send the traffic to N2, N2 might not have converged and decided to send the traffic to D. That would be bad. Then you've done your repair, and then as soon as S has recomputed, you'd start looping traffic. So instead of doing that, you can have a local hold down, which is configured on S, which tells us keep using the alternate until this period has passed, and that period is conceptually the time for the network to converge. So that's one issue with the local hold down. Now then there's another issue with your loop-free alternates which can come up, which is the alternate is pre-computed to protect against a particular type of failure. It may be computed to protect against a link failure or a node failure or both of those plus SRLGs. But if an unplanned, more severe failure happens, then you can have looping via the alternates. So in this example, S and N both have loop-free alternates which are only link protecting. So if the link from S to E were to go down, S can send the traffic to N. And if the link from N to E were to go down, N can send the traffic to S. Unfortunately, if the router E itself goes down, well, S and N cheerfully send traffic back to each other. So there are a couple solutions to this. The first one is that you can require that the link protecting alternates be what we call downstream paths. The difference between a downstream path and a loop-free alternate is as follows. The cost for a loop-free alternate, the cost for N to go back, for S to use N as a loop-free alternate, the cost for N to go to S and then to D has to be more expensive than the cost for N to reach D via its shortest path. For a downstream path, the cost from N to D has to be less than the cost from S to D. So in this particular example, S could use N as a downstream path because S's cost to D is 15, and n's cost to D is 14, but n couldn't use S as an alternate, and therefore you won't get the loop. And it turns out if you use downstream paths as opposed to just loop free, it's a stricter requirement, and you can avoid this looping concern, but it reduces your coverage. And it substantially reduces your coverage in the topologies that we've analyzed. Another method that you can do is you can use, another node protection mechanism such as nonstop routing or graceful restart to try and protect your node failures. The same issue occurs with unprotected shared risk link group failures. In this particular example, S and E and T and F are two links which are in the same shared risk link group. Maybe they're running through the same conduit. They fail simultaneously, and even though S has a loop-free link and node protecting alternate, T has the same, and they point back at each other. This problem can occur whenever the failure that happens is more extensive than the alternate was pre-computed to protect against. And you can solve this by using the downstream paths, but then you have to worry a bit about coverage. Another piece is how do loop-free alternates interact with costed-out links? So if you cost out a link in order to do some maintenance, or if it's because BGP isn't synchronized yet, you don't want to be using that link as your alternate next hop, because if BGP is not synchronized and you head over to that router, some of the BGP traffic going across there, it's not going to have a path. Similarly, LDP, if you go across a link where you don't have your LDP session up and your label bindings established, then you won't be able to send LDP traffic across that alternate. It won't be useful. So one of the requirements with the loop-free alternates, and what we have with LDP Fast-Reroute, is that it's not allowed to use a costed-out link as an alternate next hop. This maintains the idea of having the link costed out as, don't send me traffic. Don't send traffic across this link. So we need to maintain that with Fast-Reroute. And the other piece is, if you look at the network and if you think about max out costs, well, if it's really expensive for the router to get to that router and it's symmetrical, then it's really likely to use that link as your alternate because it will be so expensive to come back. So let's talk a little bit about MIBs and manageability for this. For loop-free alternates, there are a number of different MIBs which are needed. Basically, there's one for IP, which is just an extension to your IP routing table to tell you which routes are protected, what their alternate next hops are, why routes aren't protected, give you some summaries so you can monitor what the protection is. You want to do the same thing if you're protecting LDP traffic with an extension to the LSR MIB, and then have, again, extensions to your IGP MIBs to report what the behavior is on a particular area or level. What type of fast reroutes configured, how many times the single failure assumption has been violated or was valid, these sorts of things. And more input on what would be useful for manageability would be very welcome. So for basic troubleshooting on your alternates, well, you have your show commands, you have your MIBs in order to tell you which next hops are used for each route. But the alternate next hop is only used for a short period of time, and you may still want to verify the functionality. Now, you can extend ping and trace route very straightforwardly to send traffic across the alternate next hop to see what path it's going to take. Now, of course, the path that it takes depends on what the router's downstream does. So if you have it won't show you what would happen if you had a node failure instead of the link failure it's protecting against, but it will show you the path that can be taken. For network coverage for loop-free alternates, as Dave said, the existence of the loop-free alternates depends very strongly on the network topology. And if you do minor changes to the network, that can lead to substantially improved coverage. The analysis, this is the networks that I had available, showed that basically about 79–80% of source destination pairs could get protection using loop-free alternates in ECMP, which left about 20% unprotected. So where is this work currently? We're working on standardizing it in the routing area working group in the IETF. There's a framework draft, which Mike Shan's written. There's the loop-free alternates draft, which I've worked on. And then there are a number of different competing drafts on advanced mechanisms which could be used in order to improve coverage. One of them is talking about U-turn alternates, which I'll go on to explain. One is talking about the idea of the loose source routing that Dave referred to, basically using IP tunnels and something called directed forwarding. I'll explain when we get there. And then the third idea is, well, you can use TE tunnels as alternates to augment your topology. So let me talk about U-turn alternates briefly. The basic idea here is if you don't have a loop-free neighbor, then, well, one of your neighbors is sending the traffic directly to you. And if you could just tell that neighbor not to send it to you, back to you, and send it to its loop-free node-protecting alternate, you'd have a way of getting beyond your immediate neighbor. So in this example, S has the link between S and E fail. Now, S normally couldn't send traffic to NI. NI isn't a loop-free alternate because NI sends the traffic to S. But NI has itself a loop-free node-protecting alternate going to R. So if NI is capable, anyone is capable of breaking the link and has told S that, then S can send the traffic to NI. And then NI, instead of sending it back to S, i.e. the primary neighbor from which it got the traffic, it can send it to R. And then R is on the shortest path. R's shortest path to the destination D doesn't go through S, and also doesn't go through the link between S and E, or E itself in this example. Another point, the U-turn traffic, i.e. S sending the traffic to N, can either be implicit, i.e. hey, that came from my primary neighbor, I'm not sending it back there, or explicitly marked, so S can explicitly tell N via a label, as one label regardless of which prefixes, etc. It's just a flag saying, hey, I'm sending you this traffic, I expect you to send it to your alternate, not back to me. The mechanism with U-turn alternates, it allows S to direct the traffic to join the shortest path tree at its neighbor's neighbor. So essentially it extends the reach of the mechanism. And what I found is this can substantially increase the coverage in real topologies. So now from 79.5%, 80%, it goes up to about 98.5% coverage. Now, to do U-turn alternates, you do need to signal the U-turn recipient capability, i.e. The router's neighbor has to say, I can break loops before you can send it this traffic. It gives you protection of your LDP traffic without any additional LDP sessions or extensions. There's no extra management for that. And it has the same additional computational complexity as for loop-free alternates. I'll get into the computational, how feasible it is to compute these different methods and give you a sense of what their cost is in that regard in a little while. And if you wanted to, you could cascade the U-turn alternates to get better coverage. It's, again, a cost benefit trade-off. How much extra complexity do you add in order to get the extra percentages of coverage? So you've got basic configuration options. One of the goals with IP Fast-Reroute is to have it pretty straightforward to configure and operate. Obviously, plan, see where the stuff goes. That's a little more complicated. So you basically configure per area. You can enable it. You can enable loop-free and U-turn or just loop-free. If you've enabled loop-free, then you won't have any of the signaling extensions that you need for U-turn. You need to specify your local hold-down timer, which I talked about, and that continues the use of the alternate into the new primary is safe. And you can also specify whether you want to only use downstream paths for link protection or whether you'll allow loop-free alternates for link protection. And then per interface, you can say, don't use this interface as an alternate, and you can also configure whether it's U-turn recipient capable. So that's U-turn alternates. Now let me go on to another idea. The concept is basically loose source routing. So it would be useful to have loose source routing in order to be able to route around a problem, i.e. the failed link or node. But there's no hardware that really supports real loose source routing. You have to go to explicit routing with TE and MPLS. But you can approximate it in IP using tunnels. So you can put a tunnel on and say, get me to this next point. And then from that next point, can safely get to the destination without going back through the failed link or node. And usually one intermediate destination or waypoint is all that's needed. But sometimes you need to do more. And sometimes you need to get the packet to the neighbor of the waypoint. So then there's an idea called directed forwarding. So basically, the goal for this approach has been to get 100% coverage without asymmetric link costs. And with the approach they have, you can do it. It uses IP tunnels combined with directed forwarding. Doesn't matter what type of IP tunneling you use, IP and IP, GRE, L2TP, take your pick. Obviously, it will have to get defined. But then there's directed forwarding, which lets the router specify to a tunnel egress exactly where to forward the traffic. You could do this with an MPLS label. And what we found is, what Mike Shannon and Stuart Bryan have found that have been doing this work, that link protection gives you 100% coverage. Tunnels give most of that additional coverage beyond the loop-free alternates. The directed forwarding adds the last couple of percentage for coverage for link protection. And then to get to 100% node protection, it's possible you may need a secondary repair or a secondary waypoint. It's a very small percentage, but if your goal is 100% coverage without network changes, you need to do that. And they were planning on addressing SRLGs in the next version of the draft. Exciting transition. So here's a little bit more of a sense of the pre-computed tunnels. In this example, the link that you're trying to protect against the failure of is from A to B. And even without that link, if that link fails, A can still reach Y. So it can do a tunnel to Y. Now, Y may or may not be able to reach B directly, and destinations which were reached previously beyond B. But if Y can't directly reach B and destinations beyond it, using its shortest path without going through that link, then in this example, Z can. So what you can do is have A can encapsulate traffic to Y and tell Y, send the traffic to Z. Then Z can reach B and all of the other destinations that were previously reachable via B. And when this happens, when you have the failure, A encapsulates the traffic with the label for directed forwarding and sends it to Y. Y takes off the IP tunnel and looks at the label and says, oh, this switches to Z, sends it to Z, and then Z sees an IP packet and it forwards it according to its shortest path. The third idea for improving coverage is, well, to use TE tunnels as your alternates. You can use TE tunnels to enhance your topology and provide a direct adjacency to a neighbor, to a router that could give you loop-free alternates if it were a neighbor. And if you already have TE support, well, it's a standalone solution to give you improved coverage. And it does have the benefit that if anywhere in the network there is an alternate path, then you can use an explicitly routed TE tunnel to actually provide that alternate. So now let me go in and talk about some of the implications in the forwarding for IP LDP Fast-Reroute and also contrast some of the methods. You still use your longest match tree of prefixes, and you've stored, for ECMP, you're already storing some number of next hops. Well, now you store an extra one for your alternate. And for ECMP, you pick one from your next hops. If that next hop is down, then you want to select among the next hops you have left in order to determine where to send it. And in order to get scaling and fast repair, you use BGP to IGP indirection so that multiple prefixes can use the same forwarding result. And if you can, you want to store and check the interface state in the forwarding path so that you get that deterministic failover regardless of how many prefixes are affected or how many forwarding results are affected. Now, what do you have to do in order to support U-turn alternates as far as forwarding? Well, packets which are sent to an alternate next hop may require adding an optional U-turn label, which is removed at the next router. It identifies the packet as a U-turn packet, but you don't forward or you don't switch the packet based upon that. Instead, you pop off the U-turn label and do the forwarding based on the MPLS label or IP header underneath. And if a potential U-turn packet would be sent to the same neighbor as the packet was received from, then you select among the next hops for where to send it. And your selection is still among the same set of primary next hops plus one alternate. For the IP tunnels with directed forwarding, for forwarding implications, you may require multiple encapsulations, a directed forwarding label, an IP header to reach the final waypoint, and potentially for some of the node repair, you may need a second IP header to reach a middle waypoint. Now again, to get from like 80% up to 98% or so, just one IP header to get to a final waypoint works. And then if you add the directed forwarding label, that'll get you to 100% for link protection. It's when you then need node protection, you may need, for a very small percentage of the cases, a second IP header. And then if you start considering SRLG protection, it's possible you may need some more waypoints. Mike and Stuart are still investigating the methods for applying SRLGs, this approach to SRLGs. And then multi-home prefixes could require an additional tunnel. So you can sort of see one example here. You also have the issue, you need the ability at the tunnel endpoint to pop off the header and do, two lookups potentially. So that's forwarding implications. Now we talk about the computation, because obviously, in order to do any of these approaches with IP Fast-Reroute, you have to do a bit more than just a single SPF computation. So, in the first case, you just do one SPF computation normally. This is for your primary paths. You route that at S. Now, in order to support loop-free alternates, you have to know both how your neighbors get to the destinations, so you need to do an SPF at each of them. And you also need to know how they would get to S, because you need to know the cost from that neighbor back to S. So you do a reverse SPF rooted at S. So that's just where you swap the link costs and run the same SPF algorithm. So in that case, in this particular example where S has 3 neighbors, you end up having to do 5 different SPF computations in order to be able to compute your loop-free alternates. Now for U-turn alternates, there's, again, one additional SPF that needs to be done at each of the neighbors. You seed the SPF a little bit differently. The draft talks about that. And then with all of these, with the loop-free alternates and the U-turn alternates, the number of SPFs that are required can be easily reduced by deciding that a particular neighbor can't be used as an alternate. So if operationally you configure, for instance, that the link between S and N2 can't be used as an alternate, well, then S has no way of using N2 as an alternate, so it won't bother to compute an SPF for N2. So you can get down to 6 SPFs from the 8, and that's under your administrative control. Then there's really a destination-based computation approach, which is more the IP tunnels and also RSVP-TE tunnels. Now, clearly, you're not doing one SPF per destination. Instead, what you do is you use a proxy in order to reduce the number of SPFs that are necessary. So in this example, in order to get node protection, you use each next hop, in this example, all of the Rs, as a proxy for the destinations that are reached via those Rs. And in this case, you have to, for IP tunnels plus the directed forwarding, you need to do one reverse SPF per proxy. And that's for the simple single tunnel case. If you needed multiple waypoints, it gets a little more interesting. And for RSVP-TE tunnels, well, you have to do one CSPF per proxy because you have a path. You need to find your path to get there. For TE, because it's explicitly routed, you don't necessarily have to do this each time the topology changes. You may be able to leave some of them alone. But regardless, there's no configuration to reduce the number of SPF computations that are required in this approach. It's based upon your network topology. Okay. And there are some issues with proxies. The primary one is not uncommon. It's, how do you handle multi-home prefixes? Basically, if your primary neighbor is announcing a prefix, in this case, A is announcing the prefix, and S wants to have an alternate that protects against the failure of A, well, you can't use A as the proxy. You need to actually use the prefix as the proxy. So you can group your prefixes into sets and use those. And this is particularly important for protecting, say, area or level border routers, because those are the ones where you are announcing multi-home prefixes, also internally, of course. So just to summarize the comparison between the different methods. Okay, with loop-free alternates, the number of SPFs is basically 2 plus the number of neighbors you have. And there's no encapsulation overhead. It gives you about 80% coverage. It's topology dependent. If you want better coverage, you can design your topology to take this into account. And the complexity is relatively low. For U-turn alternates plus loop-free, well, you need 2 plus 2 times the number of neighbors for SPFs. That's the number of neighbors that you're willing to have be used as alternates. For encapsulation, you either need none or 1 label. And it gives you about 98% coverage. Again, topology dependent. There are certainly pathological topologies that don't work well for loop-free or U-turn. There are ones which work very well indeed. And the complexity is medium. IP tunnels with directed forwarding. Well, you need to do 1 SPF, obviously rooted at S, plus the number of neighbors, plus potentially 1 per multi-homed prefix group. As far as encapsulation, anywhere from 1 to 3 or more IP headers, plus a directed forwarding label. Now, most of them will only have 1 IP header. Some of them will have an IP header plus a label, and then a few cases will go up from there. But what you get for that complexity is 100% coverage with enough levels of tunnels. And, well, I think the complexity is high. So that covers the different mechanisms for repairers, how to get sufficient repair coverage. And now I'm going to go on to talk about the second piece of the problem, which is your micro-forwarding loop prevention. So when I spoke about the local hold down, that handles the local forwarding loop, i.e. there's a loop between the router whose adjacent link or router has failed. But there's always the case where, as Dave said, 2 routers or multiple routers which are completely upstream of the failure, or for that matter, cost change, form a loop because of the different times that they converge. So even though we've got these mechanisms to prevent the packet loss by fast reroute, you can still lose packets due to the microlooping. And if you're trying to get to 50 milliseconds or less traffic loss in the event of a failure, that's a problem because these microloops, depending upon implementation, where they are in the network, that sort of thing, can last longer than 50 milliseconds. They form when the fibs are inconsistent. If you can do controlled convergence, I have an ordered way of changing from the previous topology to your new topology, it's possible to avoid these. So we couldn't think about controlled convergence before because we didn't have alternates to use in the event of the failure. Basically, because the traffic isn't being lost, we can afford to take the time and do a controlled convergence. And you can then use a common method for both failure and management change events. Currently, of course, there is a common method for both failure and management change events. It's called do it as fast as you can. Converge as quickly as you can. Everyone else does the same, and at least you've limited the interval. Well, we can do something more intelligent because traffic isn't being lost. Of course, sometimes it's not a single failure. It's not a single link. It's not a single node that went down. It's not an SRLG. Or a known SRLG, I should say. So you want to have the traditional do it as fast as you can approach as a safe failback. So if in the midst of doing a controlled convergence, you find that there's been a problem, that a second link has gone down, you've got an unrelated LSA, then you fell back to do it as fast as possible. But here's what you can do. Here's a couple methods if you have the time, if there's been a single failure or a single change. Path locking via safe neighbors is one idea. The basic concept here is to try and find somebody you could send the traffic to who wasn't sending it to you before the change and who won't be sending it to you after the change. That's what we call a safe neighbor. So before the failure, they have to be loop free, and then after the failure, a downstream path. And then there's this 3-step approach. Now, each of these intervals that I'm talking about is essentially a fib compute install cycle. So it's you wait long enough for the worst case router to have computed and installed the information before you move on to the next interval. And I'm afraid that's a thing you need to configure. So in interval 1, you install the safe neighbors as your primary next hops. So now traffic is still safely flowing. Some of it's going to the point of failure and being repaired using the alternate. Some if it's flowing along the new primary. Along to the safe neighbor, and then so on. At interval 2, the set of routers that don't have a safe neighbor install their primary next hops. And then at interval 3, you install your new primary next hops. What this gives you is a fixed convergence time regardless of the network size. You have 3 intervals, no more, no less, and you can get the controlled convergence. And there's a draft down here to go look at if you have interest. So here's an example of the prevention for it. In this particular topology, the black arrows indicate the shortest path before the failure. The green arrows are the shortest path after the failure and the network has converged. And the sole red arrow there is a safe neighbor. This is considering what happens if the link from X to Y fails. Okay. If the link from X to Y fails, during interval 1, S starts sending traffic to F, B starts sending traffic to C, and C starts sending traffic to Z. So let's examine that. S's shortest path before the failure was via A, X, Y's cost of 4. Now, F's shortest path before the failure had a cost of 11, which is clearly more than 4. But its cost to go, it's loop free with respect to S because 11 is still less than the 14 it would have costed to go through S. And then after the failure, F's cost to get to D is 11 as opposed to, the 13 that is S's cost. So that's, one example. So you have that in interval 1. Then in interval 2, X, which didn't have a safe neighbor, sends traffic to C. And then interval 3, S starts sending traffic to B, because S in this example is the only one who was using a safe neighbor that wasn't a new primary next hop. And this mechanism avoids the microloops between S and B and between X and C. However, the path locking with safe neighbors doesn't solve loops with asymmetric link costs. In this example, R and T both have safe neighbors. S and R both have safe neighbors. S's safe neighbor is R. R's safe neighbor is T. But it's possible for traffic to loop around via S. You could avoid this if the safe neighbor constraint were stricter, i.e. if the safe neighbor had to be a downstream path before the failure, but this reduces your coverage, which is always the case with using the downstream paths instead of loop-free alternates. So with path locking, you can still get micro-forwarding loops between nodes without safe neighbors. Now, the analysis we've done of real topologies shows pretty good coverage, about 90% of the potential micro-forwarding loops. And there's a similar set of unprotected destinations for this approach as for the loop-free alternates. But the thing to remember is you can get collateral damage for protected traffic if it's going across a link which is also transiting unprotected traffic. So this is just, going through the path locking again. You get your fixed delay. You can basically avoid ordering by using transitional paths. It handles SRLGs, and actually it can handle any set of topology changes that happen within a small interval before it goes off and starts this procedure. And then in addition to safe neighbors, there are different ways of extending path locking in order to improve coverage. And, it's your favorite pick of different forwarding mechanism changes, essentially. You can use tunnels, you could mark your packets, you could break U-turns. All of these methods will give you better coverage with path locking, but they require forwarding mechanisms. And here's an example of typical coverage. In this particular instance, the links on the bottom are numbered basically according to the number of microloops potential on them. And then the magenta area there is the number of microloops that happen in the absence of microloop prevention. And then the little blue spikes are the microloops that are left after you apply the path locking with safe neighbors. So just to give you a sense of what the coverage ends up looking like. So next idea is ordered fib installation. And the idea here is to determine a safe ordering for the fib installation. For bad news, you can update from the edge to the failure. Conceptually speaking, you're peeling away the dependencies on the node before you change how that node forwards. For good news, you update from the change to the edge. Conceptually, you're creating the paths to the change. and then you only use it once the path to the change has been fully and safely created. Each router computes its rank with respect to the change, and you have to delay for a number of worst-case fib compute intervals, install cycles, proportional to the router's rank. What this means is, in the worst case, the delay is proportional to the network diameter. For the good news, the reverse SPF that you do gives the necessary depth. But for the bad news, it's overly pessimistic for some topologies. In this particular topology, for instance, there's a whole cloud of routers topped by B, which are always going to go through A, regardless of how, in order to reach D, regardless of how the topology inside changes. But A can't tell that with the computation. And the advantage here is, well, you do avoid all your microloops, but it requires a single fib install per prefix, but the delay is dependent on your network diameter, so it may not be an acceptable solution. Let's see, mostly covered that already. So just to summarize, the benefits for the ordered fib installation is there are no forwarding changes required. There's no signaling required at the time of change. You could augment this with signaling in order to try and reduce your delays. And it gives you complete prevention of loops for isolated SRLG node or link failures. The downside is it requires cooperation from all the routers to do this. It can delay your reconvergence for tens of seconds. And the SRLGs require per destination delays. So just to compare briefly, ordered SPF is a control plane only. The SRLGs do require destination-based decision, and the delay for your network convergence is high. For path locking, it does deal with SRLGs, uncorrelated changes. You can have various forwarding methods depending on the sub-mechanism you choose, if you choose one, in order to improve the coverage. But of course, the completeness depends on additional forwarding mechanisms. But the delay is small. It's only 3 fib compute install cycles. So that's the basic idea. Now Dave's going to go on and summarize and ask some of the questions that we have for you.
So we now enter the quiz part of the presentation. Just kidding. So I'm not going to quiz you, but what you can probably understand from the presentation that we've given so far is that there are a variety of mechanisms to solve this problem, all with pros and all with cons. And with these types of decisions for not only how to do IP Fast-Reroute or microloop prevention, at the IETF and here we actually need your help to figure out exactly which solution to this problem we should begin working on or continue working on, and which ones we can X out. Some are more complex, some are easier, some can be solved with probably some straightforward, simple network design changes. So let's quick review. What do these solutions cost? We are running more SPFs. Means more control plane work, more CPU, the OS is busier, we need more memory. We don't require ubiquitous network deployment, but network holes don't help with IP Fast-Reroute. If you've got a hole in the network, we simply are going to go back to the old way of converging, which can be pretty quick, but we're going back to the old way of converging and having microloops at those cases. Some of the solutions require some protocol extensions, which we may or may want to try and deploy in our networks. Some solutions require per packet marking, and not all solutions provide 100% solutions, which may or may not be a problem for what we're trying to do. From an operational perspective, it is difficult to debug during the recovery event. What are you seeing in the network? You're seeing, really you do take a look at your LSDB and you're seeing traffic going in a different direction. This can be a little bit confusing, but it is transient, and more tools would certainly need to be developed. The operational requirements, the show commands, policy filters, additional data to be signaled, configured, is not complete. You can tell that we're still really working on the algorithms, although we're trying to make inroads into some of the operational complexities through definition of the MIB at least, to be able to understand what the alternate paths and backup paths are going to be. The other thing is that you can probably tell, because we're talking about IP and not MPLS, is that none of these solutions can help you with traffic engineering or bandwidth constraints in your network when you have a recovery mechanism. This is one of the most important issues to understand with this particular technique. But as we also all know from our IP networks, we do need to understand our traffic matrices, and we need to understand how to lay out our IGP metrics always in our networks to get proper data flowing in the proper direction within the proper constraints as the network's been built. We did not discuss multicast. There are a number of proposals on the table. This is as much as I'm going to talk about multicast, but the question is, do we need to solve this for multicast or not? Multiple simultaneous failures. This is known, our solution to this is known as the runaway policy. And it's runaway policy because we can detect one failure and solve for that, but when we hit multiple simultaneous failures, I actually believe from experience, and others believe from experience, that we should just simply not try and solve that. Go back to your default mechanism, because it's almost an impossible solution set to find all of the loop-free paths for multiple simultaneous failures in the network. So let's get to the key questions that we have for you that perhaps will seed some questions back to us. Is any of this necessary? Do we, if we have sub 500 millisecond convergence and what we're worried about is determinism for trying to get below 200 milliseconds, is all of this complexity worth it or not? Second, should we if we want fast reroute, should we rely on MPLS fast reroute? We know how to do it. We know its deployment complexities, but we know that it works. What services need to be protected and how fast? Do you need to protect only strategic resources? Should we only worry about partial coverages, links instead of trying to do nodes, SRLG or not? If it's only a partial solution, what percentage is enough? Is 80% good enough? And let's use a well-known, tried and true algorithm that we know what's going to happen. We know how to build networks around it. Do we want to try and get up to 90%? Do we want to get up to 100%? How partial is partial? How predictable does the coverage need to be, et cetera? And how far of a solution set do we need to go? As part of the solution set, as protocol designers, can we ask you to modify the designs of your networks to have topologic shapes that naturally are easier to calculate backup paths? Are there any allergies, phobias, or otherwise religious problems with any solutions? That's a pretty open question that perhaps we should solve at the bar instead of trying to solve this at the mic. How understandable does the repair process have to be? That's obviously the main operational question back to operators. What debug support's needed? We need help there. We need help with multiple failures. Where in the network would this be used? Core, edge, everywhere? Is this just a strictly service provider problem? Last slide of questions. The timing of the cutover. How many stages and how quick do the secondary and tertiary stages need to be? Do we need to worry about encapsulation, misordering during the transition? How do we trade off the simplicity versus the completeness? This should be the overriding theme as you hear coming from us from these key questions. And what level of complexity do you want to trade off with a software solution versus a network design solution, which is what it says in the last cutoff question. So let me hit you with the architectural conclusions that we want you to walk away from. And there will not be a quiz on all of the techniques. We think that IP Fast-Reroute does provide a way of computing and using backup repair paths in IP networks. There's many solutions. There's going to be more emerging. And we believe that it provides a complete link node and SRLG protection end-to-end. We use a very easy, well-known, straightforward algorithm, the shortest path first, or reverse SPF algorithm to compute the repair paths. No tricks, no PhDs are required to understand these algorithms. And the last thing that we want to get across is that we are not attempting to replace, compete, or otherwise do away with MPLS Fast-Reroute. MPLS Fast-Reroute absolutely has a place in your networks. It solves different problems in different problem sets. This is just merely another tool in the toolbox to help you solve more problems and provide better levels of service. So we can take questions now, or we can go directly into, let's see the data.
I think it's best maybe to take questions now and then see the data, because is that all right with you? So is there anyone who wants to jump up to the microphone? No? Here we have some people raising their hand, coming down the side aisle. So we'll go there first and then to the center.
Hi. Yeah, this is Livio Riccioli from Meta Networks. How do you define the failure? In other words, could it be an intermittent failure? Could it be just a loss of some of the performance parameters that were agreed on? So, and how does that definition impact the rest of what you talked about, in other words, of the repair process and the convergence to the new topology?
Very good question. The answer should be kind of clear. It's complete failure of the forwarding plane either due to an adjacent link or a remote node or link failure going down. Because there's no traffic engineering parameters passed around in pure IP networks or in internal gateway protocols that is not associated with MPLS, we have no way at this point, within protocol specifications, to actually move traffic due to a congested link. Right now, we're only talking about complete failures of both links nodes. Alia, do you agree?
Yeah.
Okay. Did that answer the question?
Yeah. So suppose there is an event like a flooding attack or some other intermittent failure. So can you comment how that will impact your sort of handling intermittent failure of that particular link?
So any attack or intermittent failure is only seen as a complete failure if it's able to tear down the adjacency or otherwise make the node appear that it's gone away. So any transient failure will have us kick in completely towards a full recovery and then recalculation. When that node or link comes back in, we make yet another full recovery and recalculation of what's available in that network. Vijay?
Okay, thank you. So,
Vijay Gill, AOL. One of the things we've noticed is that most of the solutions proposed here seem to have a very high complexity versus benefit trade-off. And as a result, we are not sure that we can either deploy those and debug those at the same time. And I mean, having worked at several large ISPs, I can safely say that we can barely run our networks today. For example, Dave, you should be familiar with the IBGP withdraw bug at UUNet, which took us 2 years to solve. So I'm not sure whether this will help us or hinder us in the long run. And the second point is that sub 200 milliseconds should be more than enough for pretty much anything. People that claim that they need 50 millisecond restoral because they must emulate PSTN, I have only one thing to say to them. Look at the take rate of cell phones versus wireline. Cell phones are nowhere close to providing the quality of wireline. However, they're convenient and they're cheap. And as a result, people will tend to migrate towards services that are good enough as opposed to perfect, because the cost of getting to 100% is more than the benefit of getting to, like, say, 80%. Solve the 80% of the problem, drop the top 20, we will be fine.
Thanks, Vijay.
okay, so we'll go over here to the wall.
Yeah, Daryl Newcomb, Scenic. Doesn't any one of these solutions explode the fib, at least for some of the routers, if you're doing it on a per prefix basis, per input interface, per tunnel?
Well, it doesn't explode it. There's no doubt that you're going to use more memory trying to hold backup paths. There's no doubt about that. It will take more memory. The actual implementation of how you can use that memory or reuse objects within that data structure is implementation specific, but without a doubt, it'll take more memory. And of course, the memory that it's using generally for the next hops is greater than a node in a tree structure. So you are using more of the larger uses of the memory. There's no doubt about it. But it is kind of implementation specific on how much you can shrink down that impact. It's kind of the same problem that we see with any backup strategy. When we brought in MPLS Fast-Reroute, we use more memory as well. But it's how you can use that memory most efficiently in your implementation. Hope it helped.
Hi. Dan Golding, just a couple of comments. First, you guys had some questions. One question was, are enterprises interested in this? I think we can pretty safely say that enterprises would be interested in this, but remember, the percentage of enterprises that use MPLS, if there are any MPLS dependencies, is exceedingly small. One other point is, this kind of goes back to the good enough, better, best thing. I back up what Vijay says. It's important to do 80% and have this so you can troubleshoot it, rather than do 100% and make it so complex that troubleshooting is impossible, because you have to assume there are going to be problems that will need to be troubleshooting for. So as every kind of deviation of completeness gets done, it's harder and harder to troubleshoot and more complex. So it's better to just kind of get good. And I guess the final question is on 50 milliseconds versus 200 milliseconds versus 500 milliseconds. 50 milliseconds, people are just parroting when they say that. I mean, they say, well, sub 50 millisecond convergence time, that's just a sound bite. But in terms of enterprises and their requirements, they do have realistic, kind of 200 millisecond requirements just because they frequently have applications, call center applications, legacy mainframe applications that are just really finicky. But I think with 200 milliseconds, you're fine.
Thank you. As you know, when I started the talk, basically I was trying to say that I agree with that point. But unfortunately, every time I go out and talk to service providers or operators or enterprises privately and say, you don't need 50 millisecond recovery, they say, well, we don't need you. And so we've got to think through and at least provide the solution set so people can understand the complexity trade-off of what it's going to take to get down to the 50 millisecond. But we really appreciate the feedback.
Okay, thank you. I think now